Okay, so we on to section 3.6, trigonometric functions. And the theorem just gives us the derivatives of sine and cosine. And with these two, we'll be able to derive the derivatives of tangent, cotangent, secant, cosecant by simply applying the rules that we learned before for the first exam, namely the quotient rule. But so we need the derivatives to know the derivatives of these two functions, cosine and sine. And yeah, I mean, this is something we just need to do. We need to learn this in order to add this to, I mean, when we need to be able to compute these derivatives that are very important, we need to add them to our set of known derivatives. We already know how to differentiate polynomials, power functions, and quotients of these functions, also the derivative of an exponential of e to the x. And now we're going to be adding many trigonometric functions. The next step, of course, will be after learning, the chain rule, which will allow us to compute the derivatives of composite functions. Then we'll be able to compute the derivatives of inverses of all the functions we know already, and we'll be able to complete our list of known derivatives. But we need to begin with this, for which we already have all the tools. And in fact, uh, coming to the formulas for the derivatives, we see here that there's some sort of asymmetry. I mean, some sort of a relation still between the sine and cosine in terms of the derivatives. And I mean, we'll see actually where this comes from, and we'll show why that is the case, and we'll put to use some limits that we computed some time ago. So the derivative of sine is equal to cosine, and the derivative of cosine is not sine but minus sine. This is something that people often make mistakes about when applying this rule in exams. So the derivative of sine is cosine, the derivative of cosine is minus sine of x. And to show what this is the case, remember there was at some point we covered the limit. We found out that the limit of sine of x over x was equal to 1, and the limit of 1 minus cosine of x divided by x was equal to 0. Well, that will actually play a role here. We also need some perhaps forgotten formulas for you. The sine of x plus y being 1. That allows us to write the sine of x plus y in terms of sines and cosines of x and y. And the same thing for, just computing the cosine of x plus y in terms of the cosines of x and y and the sines of x and y. Knowing this, how do we compute the derivative of the derivative of sine? The derivative of sine of x needs to be computed by definition. Remember the second formula that we had was the limit as h approaches 0 of the function at the point, at the point x, plus h minus the sine at the point x. Remember, f of x plus h minus f of x. All of that divided by h. And we have to compute that limit. Sine of x is nothing we can do, but if we look at the first formula here, we can compute the sine of x plus h in terms of the sines and cosines of x and h. So here we'll apply this formula when y is equal to h. So wherever it says y here, we'll just use h. So this is the same as the limit as h goes to 0 of sine of, remember we're going to be using this formula here, so sine of x plus h is going to be the sine of x times the cosine of h. Remember we're using this formula when y is equal to h, and then plus sine of h, again y is equal to h. This is h here. This is y here, so that's why we're adding y to x, and here we're adding h to x. Sine of h times the cosine of x. This minus the sine of x, all that divided by h. This is equal to, we'll split this fraction into 2 sine x times, so we'll put this this term here, we'll set this term here apart, so we'll get sine of h times cosine of x, all that divided by h, and then we'll put these two terms together somewhere else, so sine of x times cosine of h minus sine of x, all that divided by h. These two limits actually exist, so we can split them and we can compute them separately and then add them together. Cosine of x here does not depend on h, so we can pull it outside of the limit, and this becomes the cosine of x. I mean, this whole thing, the first thing becomes, the limit of the first expression becomes cosine of x times the limit when h approaches 0 of sine h over h, and then plus, notice here that sine of x is a common factor, so we have the limit when h approaches 0 of sine x times cosine of h minus 1 over h. Notice here again the sine of x does not depend on h, so we can bring it outside of the limit. We can obtain finally that this is equal to cosine of x times the limit when h approaches 0 sine h over h. But this limit here, you know already. So what is the limit of sine of something small divided by the same something small? As that something small goes to 0, that is 1. And then here we have sine of x times the limit when h approaches 0 of cosine of h minus 1 divided by h. And we also know this limit is equal to 0. This is coming from these two formulas here. Sine x over x, well, here is, actually I made a mistake here, so I wrote h here when it should have been x. Okay, so now finally we can get here that this is equal to cosine of x times 1 plus sine of x times 0, so just cosine of x. So this gives us the derivative of sine, which is the first part. This corresponds to this part here of the theorem. The second part, namely the fact that the derivative of cosine is minus sine, can be derived similarly using this formula instead. So the cosine of x plus h can be developed in this way: cosine of x times cosine of h minus sine of x sine of h. And you again need to use these two limits here in order to compute that derivative, which is not it's not difficult, but I mean now we've gone over one example. We've seen how to derive the first derivative. We then I mean there's not really anything interesting or anything worthwhile looking at. Going over the second proof. I mean the second showing that I mean that the same thing happens. I mean that we can carry out the same. There's no point in carrying out the same computation for the cosine, for the derivative of cosine. You already know how it goes. So now let's, as I said, as anticipated, I said that we're going to use these derivatives to find derivatives of other functions. So other trigonometric functions. For instance, one is that the derivative of tan x is equal to secant squared. Secant squared of x. Then the derivative of secant is secant tangent. The derivative of cotangent x is minus cosecant squared of x, and the derivative of cosecant is minus cosecant of x times cotangent of x. We'll just show how to derive one. The rest, I mean, are very similar. So let's try to show the first one. Here we don't need to apply the definition because this is already we can use the rules to obtain this derivative. So this is the derivative of sine of x over cosine of x. So what can we apply here? If you said the quotient rule, you're right. So what does it say? We have to compute the derivative of sine times the derivative of cosine minus sine x times the derivative of cosine. All of that divided by the denominator squared. Now, we just computed the derivative of sine, which we now know is equal to cosine of x, and cosine of x is just cosine of x. And now we subtract sine of x times the derivative of cosine, but we also learned that the derivative of cosine was minus sine of x. All of that divided by cosine of x squared. But here, this is just cosine squared of x. Now minus times minus becomes a plus, so we have plus sine squared of x divided by cosine of x squared, or cosine squared of x. Now, if you remember from pre-calc or algebra 2, I don't know when you when you cover these things, but cosine squared plus sine squared is equal to 1. Sine squared plus cosine squared of the same angle is always equal to 1. So this becomes 1 over cosine squared, and that is nothing more than 1 over, we can write it as 1 over cosine of x, all of that squared, and this is just secant squared of x. Yeah, what's inside the parenthesis is secant, so this becomes secant squared of x, which is what we had to prove. This is what we had to show, so we're done. And so, as I said, all the other derivatives can be derived in the same, very similarly. Now, let's try to, say, compute the derivative of f of x equals x times e to the x times cosine of x. Before, we could only compute the derivative of the product of the first two functions here, so x times e to the x. But now, since we already know the derivative of cosine, we can take the derivative of this product of three functions. And how do we do that? Well, we need to apply actually the product rule twice. So f prime of x is equal to x times e to the x times cosine of x, all of that prime. This is the same as the derivative x times e to the x prime, x times e to the x times cosine of x plus x times e to the x times the derivative of cosine of x prime. I'm simply applying the product rule. Now we need to apply the product rule again because we don't know the derivative of x e to the x. So we need to use it again. And we get the derivative of the first functions is 1 times e to the x plus x times the derivative of e to the x, which is just e to the x itself. All of that times cosine of x, and then plus x e to the x times cosine of x prime. But the derivative of cosine is minus sine of x minus sine of x and then if we put everything now together, it becomes e to the x times cosine of x plus x e to the x times cosine of x, and now this whole term here, this term here becomes a minus x times e to the x sine of x. And there's not much more we can do here. Of course, we could take out the factor, the common factor e to the x, but it would just be, it will be unnecessary, and it will just make things more complicated for you, and you'll be more likely to make a mistake. Okay, so now, yeah, so there are many things that you may be asked to do. A combination of things. As I said, now that you know the derivative of sine and cosine, you may be asked to compute the derivative of the nth derivative of sine, the nth derivative of cosine. Another thing that you may be has to do would be the simple derivatives, involving sines, cosines, and exponentials now, and polynomials, now that you know how to differentiate all these functions. The combinations of these functions, because you also know the product rule, the quotient rule, which allows you to combine these expressions into more complex ones. But you can still be the point being that you can now differentiate these things because you can break it into steps, and you know the derivative of each one of these types of functions. So one thing, for instance, that you may be asked to do would be to say compute f double prime for f of x equals cosine of x plus 1 times e to the x. So here I'm just gonna leave the details for you as an exercise, so we already know how to compute derivatives and how to apply the quotient rule, right? Hopefully f prime of x is equal to the derivative of cosine of x plus 1 divided by e to the x. So you can use the quotient rule here, and you get this is equal to, after some computations, this is going to be equal to minus sine of x minus cosine of x minus 1, all that divided by e to the x. And to compute f double prime, we need to differentiate this expression. We need to take the derivative of this last expression here. So minus sine x minus cosine x minus 1 divided by e to the x prime. So we need to differentiate f prime one time, or f another time, one more time. And here, if you apply the quotient rule again, if you trust me, you'll get 2 sine x plus 1 divided by e to the x. Okay, and this is this is it for this week. I hope that you have a good weekend.